This is Mr. Johnson with you once again. This is Lecture 17, Part 2, the quantum model as it pertains to electron configuration and orbital diagrams. All right, we're going to have some fun today. Just want to remind us once again of this great diagram here, this great table that we see in our textbook on page 295 or 303 of the ebook, which is telling us, again, the sublevels and number of orbitals that exist in each energy level. I want to remind you the first energy level has only one sublevel. It's called the 1s. The second energy level has an s and a p, so we've got the 2s and 2p. Third energy level has an s, a p, and a d, and the fourth energy level has an s, a p, a d, and an f. In the last lecture, I didn't mention that there are fifth, sixth, and seventh energy levels that electrons in large atoms occupy, and that while they theoretically have 5, 6, and 7 sublevels respectively, there aren't ever enough electrons in any atom in the universe to occupy those 5th, 6th, and 7th sublevels. So in the 5th energy level, we also only have an S, a P, a D, and an F. The 6th doesn't even end up having a 6F. There's just a 6S, 6P, 6D. And the 7th energy level only has an S and a P, which we'll see based on how the periodic table is laid out in a bit. So just thought we'd start there. So I've jumped ahead to page 297 in the textbook. 305 of the ebook, looking at figure 546 here. What this is showing us is the increase in energy that the sublevels in an atom have or can have. At the bottom of the diagram is the sublevel that has the lowest energy state associated with it, and at the top of the diagram is the sublevel with the highest energy state associated with it. As you may know, electrons will go into the lowest energy sublevel possible first. And that's true of all matter. Matter goes to the lowest energy state possible. So the lowest energy sublevel is the 1s, and that's why it fills first, as we have been seeing. After the 1s fills, the 2s fills. After the 2s fills, the 2p fills. Those are the only two sublevels in the second energy level. So after the first energy level fills, the second fills. S always fills before p. Once the second energy level is full, we go to the third. And the first sublevel, once again, to fill is the 3s. After the 3s fills, the 3p fills. But, as you heard me say in the last lecture, although the third energy level has another sublevel, the 3d, it does not fill after the 3p. Rather, the 4s fills after the 3p. And the periodic table, and the way it's laid out, is going to help substantiate that for us. After the 4s fills, after 2 electrons go in the fourth energy level, then the third energy level continues filling and finishes filling with the 3d. So it goes 3p, 4s, then 3d, and then the fourth energy level continues filling. After the 3d fills, the 4p fills with, as we know, 3 orbitals or up to 6 electrons. Then, after the 4p fills, the 5s fills. There's a pattern here. Like after the 3p filled, the 4s filled, so too after the 4p fills, the 5s fills. Same pattern. After filling the 5s, but having incompletely filled the fourth energy level, the 4d fills. But remember, there's a fourth sublevel in the fourth energy level, the 4f. Well, it also fills behind how we would expect to. So instead of after the 4d filling, the 4f fills, the 5p fills. Then we come back to the 6th. After a P, it's looking like it's often an S. The 6S fills, then the 4F, then the 6P, then the 7S, and so on and so forth. So this diagram is giving us the order that sublevels fill. It's substantiating that they don't fill in the order we might expect them to. Fortunately, this doesn't need to be memorized because, again, the way the periodic table is laid out, this pattern is substantiated. And we'll do that here in a moment. All right, I flipped my page. I'm now on page 298 of the textbook. What we're looking at, what this green box represents, is hydrogen's orbital diagram. This lecture is about understanding how to do orbital diagrams, what they represent, and electron configurations. Again, this is hydrogen's orbital diagram. We should know that hydrogen has an atomic number of 1. It has 1 proton, and that as a neutral atom, it has 1 electron. If we are ever doing the electron configuration for an atom or the orbital diagram, we assume it is neutral unless we are told otherwise. So this is neutral hydrogen's orbital diagram with 1 electron. We know hydrogen's 1 electron goes in the first energy level, and all there is an s sublevel in that first energy level, and an s sublevel only contains 1 orbital. This box represents an orbital. Whenever we do orbital diagrams, a box represents an orbital. And this is the 1s orbital, because that's where hydrogen's electron goes. In these boxes we place arrows. Because each box represents an orbital, and because we know each orbital, no matter its size or shape, can hold only 2 electrons, we will only ever at most put 2 arrows in each box. These arrows can either point upward or downward. Those 2 options represent the 2 spins that electrons can assume. This electron in hydrogen's 1s orbital has an up spin. It doesn't actually matter if the first arrow you put in the box is up or down, but what does matter is when you put 2 arrows in the same box, one is up and one is down, to represent the fact that the electrons have opposite spins. I always put the first arrow up and the second arrow down, and so does our book. Again, that's hydrogen's orbital diagram representing its only electron in the 1s orbital, which is depicted through this box here. Next to hydrogen's orbital diagram, I've written its electron configuration. Instead of using boxes and arrows, we can use these symbols to represent hydrogen's electrons. The 1 in front represents the principal energy level. The electron is in the first energy level. The letter represents that it's in an s sublevel, which we know there's only 1 orbital to, and that superscript 1 represents that there's just 1 electron in the s sublevel of the first energy level. That's hydrogen's electron configuration, and it is referred to as 1s1. All right, let's go down now and look at helium's orbital diagram. Helium has an atomic number of 2 protons, and as a neutral atom it has 2 electrons. Those 2 electrons are also in the first energy level, because the first can hold at most 2. And they're also in the s sublevel, but there's 2 of them. So we draw a box to represent the orbital of the 1s sublevel, and we put 2 arrows in there to represent helium's 2 electrons. And because they are spinning opposite to each other, the arrows are going in opposite directions. Helium's electron configuration wouldn't be 1s1, but rather 1s2, because in helium's case, it has 2 electrons in an s sublevel in the first energy level. Helium's electron configuration, again, is referred to as 1s2, not 1s squared, 1s2. As we scroll down, we see the next element on the periodic table's orbital diagram depicted. That's lithium. Lithium has an atomic number of 3 electrons. 2 of them go in the 1s. So we see a 1s orbital with 2 electrons in it. And the third electron, now that the first energy level is full, goes into the second energy level and to the 2s sublevel. There's only 1 electron in there, so we only see 1 arrow. While the boxes for the 2p sublevel are drawn, there aren't any electrons in them. And if I were doing this for lithium, I wouldn't draw these at all. I would just draw the 1s box, the 2s box, 2 arrows in the 1s box, 1 in the 2s box, and leave these out. Beryllium has 1 more electron than does lithium, which is why we see a second electron in the 2s orbital. Again, no electrons in the 2p because there's only 4 electrons total. And lithium's electron configuration is 1s2, 2s1, whereas beryllium's is 1s2, 2s2. What an electron configuration is a shorthand of an orbital diagram. What an orbital diagram is a shorthand or a model of the quantum model. So these are all just more abbreviated ways to refer to where electrons are. But when you write an electron configuration, you're meant to have an appreciation of what it represents spatially or visually. Boron, the 5th element on the periodic table with an atomic number of 5, has 5 electrons. 2 are in the 1s, 2 are in the 2s, and then after the 2s fills, that has only 1 orbital, the 2p begins to fill. And in this case, there's only 1 electron in the 2p. That electron's in an orbital all by itself. When you draw electrons in a 2p sublevel, even if there's only 1 electron in 1 orbital, you need to draw all 3 boxes to represent that this is a p sublevel. Were only 1 box to have been drawn there for boron, that would look like an s sublevel because it has only 1 electron. So you've got to draw all 3 orbitals even if they don't have electrons in them. And boron's electron configuration is 1s2, 2s2, 2p1. I flipped my page. I'm now on 299 of the textbook, or 307 of the ebook, and these are the orbital diagrams of the next 5 elements on the periodic table. Carbon is the 6th element, 6 electrons, 2 in the 1s, 2 in the 2s, and then the 5th and 6th electrons are in the 2p. What is quite important about this is to notice that these 2 electrons that are in the 2p end up in separate orbitals. There is a rule for electron configurations and quantum model that says that electrons will not pair up in the same orbital of a sublevel until there's at least 1 electron in each orbital of the sublevel. That's why these electrons are not paired up. Remember that electrons are negatively charged and are repelled by each other and want to get away from each other as well as they can. By being in separate orbitals, they're more spread out than they would be were they in the same orbital, and from an energy standpoint, that makes the atom more energetically stable. That's why they do that. Notice, though, that when 2 electrons are in different orbitals, which in carbon's case they have the same spin. So they're in different orbitals but spinning the same way. And again, I always put my first arrow in a box up to take account for that. Nitrogen has another electron in the 2p, which is why we see the 3rd orbital filled with just 1 electron. But then in oxygen's case, once a 4th electron ends up in the p sublevel, that's the first time we see electrons to start to pair up in the same sublevel. And that pattern, of course, continues as you go to fluorine and to neon. Once again, these are the abbreviated versions of the orbital diagrams, which are the electron configurations for carbon, nitrogen, oxygen, fluorine, and neon. So I'm about to take you to a periodic table that has just the last term of each element's electron configuration so we can see a pattern to the periodic table. For carbon, for example, which is element 6, it has 6 electrons, all we will see in the box for carbon is 2p2, its last term. We won't see 1s2, 2s2. For nitrogen, all we will see is 2p3, oxygen 2p4, fluorine 2p5, neon 2p6. Hydrogen, which has only 1 term, is all we will see is 1s1. Same with helium, with only 1 term, we'll see 1s1. And that will continue through the periodic table. So I'll take you there now. All right, so this is what that looks like, the last term of each element's electron configuration in the box that corresponds with that element. There's hydrogen, whose only term and last term is 1s1. Helium, whose only and last term is 2s2. Helium normally lives off to the right, but because its 2 electrons are in the s sublevel, if we put it there, we'll see how it lines up with the rest of the s block. Lithium's last term is 2s1. Its first term, of course, is 1s2. Beryllium 2s2, boron, and so on. Notice that there's a pattern here as we look at the last term of each element's electron configuration. One of those is this. These start with 1. These start with 2. These start with 3, 4, 5, 6, 7, and those are the rows they're in. Notice that all of these elements, last term, has an S in it. It's the S sublevel. The last term is the S sublevel. That part of the periodic table is called the S block. Those 2 columns represent the S block, and the last term of those elements' electron configuration has an S. It's the S sublevel. Let's jump to the far right. This is called the P block. There are 6 columns worth of P block elements. That's not a coincidence because the P sublevel holds 6 electrons. The P sublevel has 3 orbitals. 3 times 2 is 6. And notice that the numbers in front also line up with the column numbers. This has got a 2. It's column 2, 3, 4, 5, 6. The S block's principal energy level corresponds with the row it's in. The P block's principal energy level also corresponds with the row it's in. There's 6 columns of P block elements. There are 6 electrons that fit in a P sublevel. There's 2 columns worth of S block elements. 2 electrons fit in the S sublevel. Well, look at this. The middle of the periodic table, where the transition metals live, is called the D block. Not coincidentally, there are 10 columns worth of D block elements, as there are 10 electrons that can fit in the D sublevel. Notice, though, that the principal energy level number, and this is key, the principal energy level number of the D blocks is 1 behind the row they're in. These are all in row 4, yet their principal energy level number is 3. The D sublevel always fills 1 energy level behind the others. These all have a principal energy level number of 4, yet they're in the 5th row. And that pattern continues. The D sublevel always has a principal energy level that is 1 lower than the row that that element is in. We're going to deal with the F block later. It's going to be an in-class thing. But these elements that are pulled out of the periodic table that actually live right here are the F block elements. And again, not coincidentally, there's 14 columns worth of F block elements because there are 7 orbitals in the F sublevel, 7 times 2 being 14. The 4F block sits right here actually, between 6s and 5d. The 4F fills after the 6s. If we remember that order that the sublevels fill, the 4F fills after the 6s. The F block elements always have a principal energy level that is 2 behind the row they're in. The 4F sits right there, and it's in the 6th row. It's between 6s and 5d. The 5F, oh goodness, periodic table, you have a giant mistake. The 5F elements, which sit right here, are also 2 behind the row they're in. The principal energy level is 5, and they're in row 7, and they sit between 7s and 6d. So now we know that there's these blocks on the periodic table, the S block, the P block, the D block, and the F block, and I'll take you to another periodic table that has those in color and look a little prettier than the circles I just made. All right, so here that is. Again, the S block is those first 2 columns. The principal energy level is always the same as the row. The P block, off here to the right, is in orange, 6 columns worth, 6 electrons in the P sublevel, and the principal energy level number does always correspond with the row number we're in. The D block is in the middle, but the principal energy level number is 1 behind the row that it's in, or 1 behind the S and the P block's principal energy level number. And then the F block, which isn't depicted here, is extracted from this zone here, and that's the 4F, and that's the 5F, which are 2 principal energy levels behind the row they're in, or behind the S and P principal energy level numbers. Why this is so helpful is if we remember this, the first 2 columns are the S block, the last 6 columns are the P, the middle 10 are the D, and then the F block is down at the bottom, is that if we follow the periodic table from element 1 all the way to element 110, the order which we travel through these sublevels based on the way they're laid out is the order in which they fill, and then you don't have to memorize that diagram that had energy on the y-axis. The first sublevel to fill is the 1s. The second sublevel to fill is the 2s. The third sublevel, as we proceed through the periodic table to fill, is the 2p. And that aligns with what we know. After the 2p fills, the 3s fills. As we keep going, after the 3s fills, the 3p fills. And then, knowing that the 3d doesn't fill next, we see that. After the 3p fills, we know we jump to the 4s, and then go to the D block, which is always 1 energy level behind the prior S, such that after the 4s fills, the 3d fills. And then 4p, and then after the 4p, the 5s fills, not the 4d, the 5s. And then 4d, and then 5p, and then 6s, and then 4f, which we're not talking as much about right now, and then 5d, and then 6p, and then 7s, and then 5f, and then 6d, and then 7p. So the way that the periodic table is laid out, if you remember about this D and F block issue, tells you the order sublevels fill. And if that's not amazing, I don't know what is. So we're back to our book, to page 299 of our textbook, or 307 of our ebook, where we see the elements after neon with their electron configurations and their core notations, which I'll talk about in a bit. Sodium's last term is 3s1. It's in the first column. It's in the S block, and it's in the first column of that S block. Magnesium is then 3s2. Aluminum has 1 more electron, 3p1. All the way through the 3p. Argon is at the end of that 3p block, 3p6. Potassium comes next. 4s fills after 3p. 4s2. Then the D fills. after the 4s. So we're seeing these electron configurations aligning, as we would expect, with the way that that periodic table is laid out in the order that sublevels fill. So let's talk about core notation, and then we'll go to a normal periodic table that doesn't have those blocks filled in to use it to write electron configurations for any element. Rather, let's use the regular periodic table to write electron configurations from first, and then we'll go to core notation. So as we look at this periodic table, which is the one that if we get to take an AP test this year, you'll be using, it doesn't have the S, P, D, and F blocks on it. Nor is it telling us what the 1s, 2s, 2p is. But we're supposed to remember that this is the 1s. This is the 2s. Lithium and beryllium live in 2s. This is the 2p. Because you remember, the first two columns are S, the final 6 are P, and the row therein is their principal energy level. This is 3s. This is 3p. This is 4s. And then right there is 3d. So you remember that because there's a pattern and it's supposed to make sense. And then right before gallium is 4p. All right, so let's write bromine's electron configuration, element 35 from this periodic table. Let's write bromine's. So if we're asked to write bromine's electron configuration, we know we need to account for 35 electrons. When I do this, I start at the very beginning of the periodic table and imagine where bromine's first electrons go, and they go in 1s. And whenever 1s is full, it's 1s2. So the first term is 1s2. After the 1s fills, the 2s fills. So the second term is 2s2. After 2s fills, 2p fills. P always is full with 6. Then we go from 2p over here to 3s. 3s2. I'm running out of room, so I'll just continue it below. Followed by 3p6. Remember, we're trying to get to bromine. All the way through p. 3p is 3p6. Then after 3p fills, 4s fills. That takes care of 19 and 20 electrons. So 4s2. Again, we're trying to get to bromine here at 35. After the 4s fills, we fill the 3d. And the d is full with 10, or we can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 3d10. This is a 4s2, by the way. And then, once we get into the zone where bromine is, the sublevel where bromine is, we're careful to count how many boxes it takes, or how many electrons it takes to get to bromine. This is the 4p, so it's 4p1, 2, 3, 4, 5. Bromine's last term is 4p5. And that's its electron configuration as 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p5. 35 electrons. Well, as you can imagine, if you're doing this often, or you're doing it for an element like polonium that has 84 electrons, that could be kind of burdensome. And we will realize, if we don't know already, that it's really just the outermost electrons, the valence electrons, that determine how that atom will behave, what kinds of bonds it will form, and what its properties are. So what we can write is what's called the core notation, the core electron configuration, which depicts explicitly the outermost electrons and leaves those inner or core electrons. So we're going to do that for bromine. We're going to write bromine's core notation. What we do is we find the element on the periodic table, which we just did, and we go up a row and all the way to the far right-hand side. We go up a row into the noble gas, which is argon. Argon is the noble gas above bromine on the periodic table. And we bracket argon. This is the core notation again for bromine. By bracketing argon, I am saying that bromine has argon's 18 electrons where we would expect them to be, which is 1s2, 2s2, 2p6, 3s2, 3p6. We're basically, by bracketing argon, saying all of that, because there's no ambiguity about where argon's 18 electrons are. Then we pick up where argon leaves off. So by bracketing argon, I go to what the next sublevel to fill would be, which would be 4s, 4s2. Of course, we know this from above, but if we hadn't done the full first, we'd have to figure it out. Then 3d10, and then finally to finish off, 4p5. This is argon's core notation, which has the noble gas in the row above it bracketed, and then the remaining electrons as their terms. All right, so we're now going to do this for polonium. We're going to write polonium's core notation, element 84. Writing out its full electron configuration would be quite a bit of work. We'll do its core notation. One thing I want to point out, again, which I haven't stressed as much so far, is that the F block really sits here and here. The periodic table is really way more stretched out than it is, and the F block should sit between barium and lanthanum and radium and actinium. But to make it all fit into a nice 8.5 by 11 piece of paper, it was pulled out and brought down below. So please know that after 6s, after cesium and barium, you drop down here to 4f. And after 7s, once again after radium, you drop down here to thorium or 5f. Okay, so we'll do this for polonium. We go up a row, we go over, and we bracket xenon. And by bracketing xenon, we are saying polonium has all of xenon's 54 electrons in exactly where we'd expect them to be. 1s2, 2s2, 2p6, and so on and so forth. So we pick up where xenon leaves off after the 54th electron. We go to electron 55, which is in a 6s. We know it fills completely. So next term is 6s2. Then, after the 6s fills, we know the 4f fills. And when it fills in its entirety, there's 14 electrons. So 4f14. Then, as we leave the F block, we come back up into the D. And that is the 5D, because remember, 5 is always 1 behind 6. 5d10. We're all the way through the 5d. We're now into the zone where polonium is. It's in the 6th row. It's the p block, so this is 6p. And we count over 1, 2, 3, 4. The final term is 6p4 for polonium. There is polonium's core notation. And take note of that we had to go through the F block to get there. That after the 6s filled, the 4f filled, then the 5d filled, for us to finish off with polonium at 6p4. And if we go back to this table in our book and look at these core notations, we'll see that what we just learned is depicted here. That it's the noble gas for each of these elements that is the row above that's bracketed with the final term or terms after the noble gas. All right, the last thing we're going to do is a practice problem on page 300, so flip to 300. I'm going to ask you to do practice problem 1 on that page. I'll then have a solution for you, and that will be the end of our time together today. So we're being asked to write the full electron configuration and draw the orbital diagram for an atom of titanium in its ground state. Titanium. So the first thing you want to do is get out your periodic table. Try to do this with a periodic table that doesn't have the blocks on it, and write out the orbital diagram and electron configuration for titanium, and also do the core notation. Do the core notation as well to get a chance to practice that. Come back when you're done, see how your solution compares to mine. My hand's a little shaky, not the best arrows, but there's titanium over here. It's element 22, 22 electrons. We know the 1s fills first, so there's just one box because the 1s sublevel has only one orbital. The 2s fills next, also only one orbital, one box, 2 electrons in each, spinning opposite. Here's the 2p sublevel with 3 orbitals, 6 electrons total. 3s with 1 orbital, 3p with 3 orbitals. After the 3p fills, the 4s always fills with 1 orbital and 2 electrons. And then titanium, oh goodness, that's not 4p. It's 3d. Is in the D block, and the D is always one energy level behind the S, so we see 3d there. And with only 2 electrons in the 3d, they go into their own orbitals before they pair up. And as I switched my 4p to 3d, I needed to add 2 more orbitals. The D sublevel has 5 orbitals, so I needed to have put 5 boxes there. And again, only 2 electrons, and they're each in their own orbital. So the last sublevel to fill is 3d. If I convert this to the electron configuration, I've got 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, finally 3d2. And if we were to do the core notation, and we were to have done it without the full electron configuration, we would go to the row above titanium, bracket the noble gas, argon, so I would be bracketing argon. I pick up where argon leaves off, which is at the 4s here, and then go 4s2, 3d2. And again, bracketing argon is the same thing as saying all of that. So there is titanium's orbital diagram, full electron configuration, and core notation. It's been a pleasure serving you once again. This is the end of Lecture 17, Part 2. It's 2:36, the day before Thanksgiving. I'm about to go start making some food and trying to enjoy my holiday weekend. I hope you can as well soon. Take care, everybody. Have a great weekend.